Hydrology, Chapter 7, Lecture 1, Runoff. Now it's getting interesting. I'm Dr. Marty Matlock. Let's get started. The hydrologic cycle and humans. Really, it is all about runoff. We've talked about infiltration, evapotranspiration, precipitation, all the processes that are driving the hydrologic balance. Now we're getting to the point where water runs off the land. Q, which is the amount of water running off the land, is precipitation minus evapotranspiration minus infiltration minus change of storage. If it seems like I'm being redundant with this particular balance, it's because I am. This is what most hydrologists have tattooed to the underside of their arm. It is the most important relationship that we understand in hydrologic systems. We're going to be working on surface runoff and stream flow over the next several lectures for the rest of this session. Remember, effective rainfall is the amount of rainfall that runs off. It's also called Hortonian flu after Dr. Horton. The rainfall amount that results in surface runoff is effective rainfall. Precipitation that exceeds all abstractions is effective rainfall. Remember, our abstractions are ET, infiltration, change in storage. We've evaluated how this happens over time and how you have this sort of buildup once the rainfall starts, where storage occurs in the soil, and then in soil depressions, and then the water runs off. That lag time between the time of rainfall and the beginning of runoff is a critical variable, and it characterizes most basins. Saturated overland flow occurs when subsurface flow saturates the soil near the bottom of a slope. This is different than just normal flow. This happens when at the bottom of a slope, saturated flow seeps back in, and you have this sort of unsaturated flow at the top of the slope. And at the bottom of the slope, you start to see saturated flow. Now, in the Ozarks, where we have hills in the Ozark Plateau, this is very common. These can be seeps in the hillside. They're also very difficult to manage if you're trying to build things on these seeps. So understanding how water moves across the hillside is critically important. The velocity of that subsurface flow is very slow. It's governed by Darcy's law, where Q, the rate of movement, equals minus K over the change in height versus the change in distance. That's Darcy's flux, the movement of water through soil, which we will return to extensively when we dig into groundwater. Yeah, that was a pun. Overland and saturated overland flows occur on the watershed, in the subsurface, and on the surface. And the water bodies, the streams, are an integral part of that. So you can see that the areas around the streams, because these are the low-lying areas, are the ones that have this zone of saturated soil that tends to stay moist even after the rainfall stops. And this is what feeds our streams in the summertime, during dry periods, feeds them water. Now let's go back a little bit to our climate classifications. The Köppen climate classification system is one of the most common ways that we classify where we live. We happen to live in a humid subtropical climate that's typically referred to in the temperate zone as CFA. And this subtropical climate is fairly unique in the southeastern United States. There's an analog for it in China, actually, the eastern edge of China, but otherwise, and a little bit in the sort of south central Africa and southern South America. But it's relatively unique because of the weather patterns and the way water moves through the atmosphere and then onto the land, and the relationship of air temperature and air humidity with the land. But for this region, we know that water has formed the land in very predictable ways. In humid regions, stream channels cover up to 5% of a catchment by area. During a rainfall event, this can extend to up to 30% of the catchment area as the soil moistens away from the channel, as we saw in the earlier image. Soil drains very slowly over time, so water in that unsaturated soil only moves about 50 centimeters per hour. It's a very slow moving thing. And that's pretty fast for subsurface. That's half a meter in an hour. About 48 hours after a rainfall event has ceased, gravity will have drained the larger pore spaces in soil, returning the soil to field capacity. The impact on surface flow is that subsurface flow continues or contributes to stream flow long after the rainfall events and the overland flow have stopped. Those are seeps and springs in the terminology of the haulers here in the Ozarks. So we see this water moving over the landscape. It moves down the slope, but it also moves laterally, but also down the slope perpendicular to the isopleth lines, which is to say downhill or down gradient to the rivers and streams. So you see these sections of a reach of a river, A, B, and C. You can see that they contribute individually to the stream flow in the channel over time, but they accumulate to create an outflow hydrograph because water from A, B, and C are all adding up, so it stacks up. And that's the way you would characterize these in an Excel file. You would simply have the staggered start lines, and they would add up to be cumulative flow. The shape of the watershed is critically important too. You can have sort of elongated or circular watersheds and everything in between. So for elongated watersheds, the length of flow of travel affects how fast water comes off. The longer water has to travel, the longer it takes for the peak of all the water hitting the soil as rainfall to come out in the stream. The shorter travel and the more compact or circular the watershed is, the circle is the most compact or efficient geometric shape, gives you a very fast runoff event, very efficient in terms of moving water out of the system over time. Surface flow accumulates as water moves down gradient to form rivulets in the soil. These converge over space and time to form channels. Channels erode into the soil until they reach a less erosive layer, such as clay, slate, limestone, granite, or other rock. The channels become streams and rivers and flow down gradient to a larger water body, such as a lake or ocean. The measures and descriptions of geometric characteristics of the catchment are based on morphometry. When geology is included, this is referred to as geomorphometry. It's a fascinating field of study. Thompson describes it very well in Hydrology for Water Management, and one of our other authors does as well. I strongly recommend you consider these books as references. Stream order within the catchment is the way we characterize a stream, and understanding the order is a way to understand common characteristics of a system. Stream channel networks have been organized into hierarchical systems for hundreds of years, from upper tributaries to the lower catchment outlet. The most commonly used system today is the Strehler method, the Strehler stream ordering procedure. We call it the Strehler method. The smaller perennial streams, those are the ones that flow year-round in a catchment, is given in order of U equals 1. When two first-order streams, U's equal 1, channels converge, they become a second-order stream, U equals 2, channel. So the channel only increases when two channels of the same order converge. You can have all the first-order streams hitting a second-order stream imaginable every 20 feet, and it won't make it a third-order stream. Not until another second-order stream converges with it does it become a third-order stream. So this process is fairly well known, fairly intuitive, but you can see the dendritic network that a fourth-order stream generates very quickly, where it has a number of second-order streams coming in, and this third-order stream doesn't become fourth-order until these two third-order streams hit. So you have a third-order stream here, a third-order stream here, because this is a second-order, third-order stream here. So two third-order streams converge, and this becomes a fourth-order stream at this point. So first orders become second orders converge with other second orders, become third order. Third orders converge with other third order streams to become fourth order at this point, all the way down. And you can imagine then large continental stream networks, you can get 7th, 8th order streams, but after that it's a little hard to get much larger. The bifurcation ratio, R sub B, is the ratio of the number of streams of a given order, N sub U, divided by the number of streams of the next highest order, NU plus 1. Bifurcation ratios are generally between 3 and 5, except in weird systems. And there are weird systems out there, deep canyon systems or hard rock systems or other systems that are not what we consider to be standard or frequently observed phenomena. Horton's law of stream numbers, there's Horton again, states that the number of streams of a given order forms an inverse geometric sequence with that order, where K is the highest stream order in the basin. NU equals R sub B K minus U. At a certain scale, drainage networks have a fractal or repeating pattern, and they are fascinating to observe from space. They are phenomenal. We've observed these phenomena on Mars. We've observed them on Jupiter, on Io, because things that flow in the same way. Thermodynamics is fairly universal across the universe at superatomic levels. The fractal nature of these systems are often a characteristic of the geology and the slope and the history of the systems. And that's what these ratios are telling us. As we talk about water morphology, it's time to start learning about streams. Stream lengths are measured by the deepest part of the channel, the Thalweg, or German for valley way. Thalway. The valley way is the boundary line where rivers or lakes divide nations and states. So if Oklahoma and Texas are divided by the Arkansas River, the Thalweg is what defines what's Texas and what's Oklahoma. Thalwegs change as streams and rivers change, however, which makes them difficult sometimes because nobody likes to lose land. We typically have a stream channel that's defined by a scarp, the Thalweg, and a floodplain. So these are typical cross sections of a stream. And the stream cross sections, here A to A prime and B to B prime, often look different based upon the flow regimes. See where the Thalweg is deeper in this outer bank? It's because it comes along here, it collects velocity, and then it hits this outer bank, and at high velocity it has to turn, it has high erosive potential. So it picks up a lot of material, then it drops it off here. And so that's then the slow-moving water of the inner part of the curve deposits material too. So you end up with these gravel bars or point bar deposits along the inner parts of these curves. And you have riffles connecting them. So you have a riffle run pool system in this sinuous river system. The length of the stream is L sub S. The length of the watershed or catchment is L sub W, measured from the stream outlet Thalweg up to the end of the largest stream, or the longest stream to the highest point away from the outlet. It is not a straight line. The centroid of the watershed, that's the midpoint X and Y axis, is L sub C. That's the center of the watershed. It's the sum of all lengths of all channels in a watershed, L sub T. The drainage density is the length of streams divided by catchment area. D equals LT divided by A. The maximum length of overland flow, L sub G, is the maximum distance water has to travel before it reaches a stream within a watercourse. There are infinite possible measures of this dimension, but there's only one L sub G bar for a watershed. Since it's half the distance between channels, it can be approximated by 1 over 2D, where D is the density of streams. This is a critical measure and is used extensively in calculating flows within watersheds. The shape of the catchment determines the rate of accumulation of runoff into the river, as we discussed before. So we have lateral flows into the channel, and you have rainfall intensity hitting an infiltration as flow drops over a given gradient, typically a slope. So in this case, L sub A is greater than L sub B. The length of flow to the outlet of A is greater than the length of flow to the outlet of B. and that creates this longer peak flow duration. Larger catchments have less uniform rainfall across the area because it can rain in different places. So you can get rain in subcatchment 1 early, then the storm moves up to 2 and then up to 3, and you can end up with these multiple peaks on the hydrograph. Now they can add up, and the rainfall looks like this, one simple bar in the rainfall hydrograph. By the way, when we plot these, it's hard to do this in Excel, so we typically plot these all on the x-axis in Excel bar graphs for the rainfall and line for the runoff hydrographs. So in the U.S., we have gauges at the outlets of many, not all Huck 8 watersheds, which can be as large as 5,000 square miles. So we monitor these things, but monitoring them is not enough in most cases. So that's why we have to start simulating them, and that's what we'll talk about in our next lecture. There are a number of resources for you, again, based upon the resources of the previous lecture. Please take a look at these readings, and I'll look forward to seeing you in the next lecture.